Alright, this is last part of lesson 1, section 3. Alright, intro to logic gates and data sheets. Alright, so we've been talking about our AOI logic, right? Our 04, our 08, and our 32. Alright, but we're going to talk about how we actually, pull up a company's data sheet. How do I know, that pin 7 is ground, pin 14 is VCC, and what the inputs and outputs are, whether we have 2 inputs, 1 output, 3 inputs, 1 output, that sort of thing. Okay, so let's take a look at it. Well, there's 2 major kind of transistor logics that we go through. Okay, so the chips that we use in class, we use TTL logic, so those are the 74LS, then whatever number we have, 08N or 08P or 32N, those sort of things. Those are called TTL logic gates that we use, and when you use multisim, remember that that's going to be under the TTL. So what is that? That's transistor to transistor logic. So that's what TTL is. Alright, some other ones that we can breadboard with if we have our complementary metal oxide semiconductors, or CMOS. Okay, so those are the 2 major technologies that we use in order to do electronic switching to get our 1s and 0s, all of our binary code. Okay, we have different types of scale of integration. Integration, not in calculus terms, but in terms of how many circuits or how many different chips that we're using. So we have small scale integration, medium scale integration, large scale integration, and very large scale integration. Okay, so that's what we're looking at with those acronyms, right? SSI, MSI, LSI, and VLSI. And then we're going to talk about a couple other things. These are going to be majorly like your vocabulary that you're going to kind of need to know when you take your test and that sort of thing. So we have through-hole technology, THT, all right, dual inline packages, surface mounts. I passed around surface mounts in class, so we kind of know exactly what surface mounts look like. Okay, so TTL, okay, transistor logic. Those use bipolar junction transistors. Those are BJT transistors. All right, there's a couple different kinds we can have. We can have NPN or PNP. That stands for negative, positive, negative, or we have positive, negative, positive. Okay, and that's really what those gates are. We have a collector, base, and emitter. So in the upper right-hand corner, you kind of see what a BJT transistor symbol looks like. All right, and we use those to do a lot of electric switching. Same with the MOSFET transistors. Alright, so the BJTs, those are going to be more silicon on the inside, and we charge that silicon with positive or negative, okay, protons or neutrons, to make sure that we can control how the electronic switching goes. So the advantages for our TTL logic is they're faster than CMOS, and they're not as sensitive to electrostatic discharge, which means they can come within like a magnetic field a little bit better. They won't disrupt them as much. The only disadvantage for those are that they use more power. Alright, so the CMOS semiconductors, okay, so the complementary metal oxide semiconductors, or the integrated chips that are MOSFETs, alright, they're metal oxide. It's really the material that they make them out of. So they're field effect transistors. They use less power. That's really the only advantage for them. They are a little slower, and they are very sensitive to static discharge. Now, when I was talking about all those acronyms earlier, all right, SSI, MSI, LSI, you guys can read all those, okay? But when we're starting to talk about those, it's the number of gates per integrated circuit, okay, or per IC. So less than 10. Those are ANDs, ORs, NANDs, XORs, inverters, those sort of things. If we have medium scale integration, is when we start adding in flip-flops, adders, counters, multiplexers, demultiplexers. Then we can get into LSI, start adding memory. Okay, so our programmable stuff, a little bit of some of the boards that we're going to use as we go through there. There's FPGA boards that you guys are going to learn to program later on in the semester. So we're going to go through and take a look at those. Okay, that's where memory starts to come into play. All right, and then if we look at the ULSI towards the bottom right, we got 8 and 16-bit microprocessors. So those are where we're going to start talking about our Arduino boards, later on when you guys do the bobots with the Adreno boards later on, like next semester. Okay, that's where those will come into play. And then we have our GSI, all right, our gigascale integration. So I want you to start thinking the motherboard on your computer or your laptop, things like that. So number of gates per integrated chip and how much is actually on there. All right, so if we want to take a little bit of time to kind of go through these, the through-hole technology, THT, the dual inline package, that's what we use, okay, with all the breadboarding that we've done so far, and some of the soldering stuff that we've used. We've been using the through-hole technology, right? We solder in the chassis and then we put the chips in the chassis. Okay, that's the most common one that you can use for breadboarding. And then I've passed around in class the surface mount technology over here on the right. Okay, and these are all on your assignments, so make sure you're taking notes on here. What a quad flat pad looks like, okay, what a plastic lead chip carrier looks like, and all those different things, okay? But these are the difference really between the two, what's on the left and what's on the right, is everything that we use on the left, for the most part, that's for us to breadboard, build prototypes. You will see a very small amount of that, like on your motherboard, on your computer, or in your TV, any of that sort of technology. Or everything on the right, that's what's going right in your phone. Most of that's on your laptop, most of that, in your computer and things like that. That's where the majority of that stuff lies. Okay, so through-hole technology, just kind of basically talk about this is our proto board stuff that you guys can put in. You can solder, make all the connections, and you guys can test and build prototypes. Okay, the problem with them is they're large, right? So you're not going to stick a bunch of those inside your phone or laptop or things like that, because they start taking up space and weight and all those different things. Okay, and most high-end electronics that we use now, they're not available in those type of packages. So surface mount, they're just much more smaller. That's really where the technology comes into play, is the surface mount, right? Instead of us having a desktop or a laptop, we can now put it all on our phone, carry it around in our pocket. Or now we have smart watches, all right? They can do almost the same thing that your phone can do, to an extent. So that's really where the surface mount technology comes in. Very, very, very small, very sophisticated, all right, and we can fit a lot more on. You don't prototype with surface mount technology. You mass produce and you sell so that you can make a lot more money off of things. You still prototype, all right, with the through-hole technology. So what we need to look at here, all right, is we got our TTL sublogic families, our logic subfamilies as we go through this. So our normal ones, all right, are the 74 series, or the 74L, or the 74S, or the 74LS. Okay, so the very first ones really developed were the 7404. Those were the original transistor logic gates. They're the lowest. They used a lot of power. They're obsolete. You're not going to find them anyways. The 74LO4 models, okay, those consume less power than the standard, but those are still obsolete. And then we have the Schottky, okay, the 74SO4. Those are kind of the precursors to the ones we're using right now. They were optimized for speed, but they still consumed a lot of power. And why is power a main concern? Because heat. So there's a lot of, your computers inside there, we got fans. We go and evacuate the heat, because heat is a negative impact on our electronics. So it's very, very important, all right, that we get speed with less heat, and that's really kind of what we're looking for, because heat will shut them down. So we got to put fans in your computers, and we cool all of our electronics, because the output from the power and the electron flow, that's all heat. All right, but what we use is the low power Schottky. All right, those are the 74LSO4. So as you've been wondering, is we've been using multi-sim and doing a little bit of breadboarding with some of these and doing the AOI logic, you're like, why is it called a 74LSO4? Okay, so that's really where it comes from. Okay, they're faster, they're low power consumption, and that's what we use throughout the course, and that's what you're going to be breadboarding with. All right, taking it up to the next step, we got the 74ASO4. Those are very fast, but they use a lot of power. Okay, so the advanced Schottky, we don't use any of those. And you can kind of read the last one, right? It's very good power ratio, quite popular and that family is the 74ALS04. We only have the 74LS04, and then we have the N's and the P's, right? Those are just kind of how they're neutrons, protons, how they've kind of adjusted the silicon stuff inside of there for the most part. Okay, and then you guys got to remember what an 04 is an inverter, and what's a 32, what's an 08, and those sort of things. Okay, so where does that come from now? So we have DM74LS08N. Alright, so for the most part, when you guys have been using multi-sim and choosing one, you've been choosing like a 74LS08N. Okay, what does all this mean here? So if we break this down, the first part of the tags, and most of this stuff is stuff that you're not going to see this in multi-sim necessarily, you're going to see it on top of the chip. On top of the chip, right, if you turn it at the right angle, you can see all this information. It's going to say DM74LS08N. Okay, so DM is the manufacturer. The manufacturer that represented by DM is called Fairchild Semiconductor. Don't ask me why Fairchild Semiconductor uses a D and an M. I couldn't tell you that. Same reason Texas Instruments doesn't go by TI, they use SN. I have no idea why that was developed that way. Okay, the 74 series, okay, that's just telling us what it is. That's TTL logic. Okay, the LS stands for the low power. Okay, it's a Schottky low power. The 08, that's the gate type, okay, or the logic function. So we have the 08's the AND gate, the 32's the OR, the 04's the inverter. All right, there's going to be some other ones we talked about. We got a 74, that's a flip-flop, okay? And then, like I said, the last thing can be an N or a D. It's how they work, their protons and neutrons and things like this. But this is an N, it's a dual inline package. It's how it's laid out on the inside with the TTL logic as you go through there. Okay, so what do we need to find on all these? We're going to look through manufacturer data sheets. So you guys are going to have to download some, keep them with you so that you can reference these when you're doing all of your breadboarding. Okay, I've kind of guided you through in class so far, and we've breadboarded some, with me there. We've used a specific AND gate, a specific OR gate, a specific inverter to do a specific task using your breadboard companion. Okay, but we want to get more in depth with these. All right, so what are they going to do? They're going to give you the pinout diagram. They're going to give you the function table. They're going to give you like the optimal operating conditions, the different electrical characteristics. Okay, it's switching dimensions. So we can look at the different things. So there's going to be a general description that talks about the gate. All right, you're going to get your connection diagram. It shows where everything is. So like the general description here, all right, this is important because this is a quad 2 input AND gate. So this is a 2 input AND gate. That's what we've been using. There are 3 input and 4 input and that sort of thing. There's multiple input gates that you can use. So it's important that you read the general description there. That it's an AND gate and it has 2 inputs. Okay? And then we can take a look at the connection diagram. So this part's the very important part, right? Understanding which is pin 1, 2, 3, 4, 5, 6, 7, because 7 has to go to ground, 14 has to go to VCC. And then we can see here, right, this is how I kind of helped you guys do your breadboarding at first. We know that pin 1 and pin 2 are inputs, pin 3 is an output, pin 4 and pin 5 are inputs, pin 6 is an output. We can see that 9 and 10 are inputs, 8's an output, 13 and 12 are inputs, 11 is an output. So that comes in very, very handy when you guys are doing your breadboarding. Okay, we can look at the function table. So if we zoom in on that, it's a truth table. It's essentially what we've gone over. So LL stands for 0, 0, right? So anytime you see L, it's a 0. Anytime you see H, it's a high, which is a 1. So this is really representing our truth table that we did on the board. 0, 0, 0, 1, 1, 0, 1, 1. Okay, so logic low, logic high. And we can look at the output, right? The output would be low, 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 high, or 0, 0, 0, 1. So that's our AND table. This is exactly like the one we did in class together on the board. Okay, we can look at the recommended operating conditions, and this isn't going to be important on your homework assignment because you're going to actually have to pull up the data sheet for a specific circuit, or essentially, and answer a lot of these different questions. So you want to look at I might ask you to find the maximum operating supply voltage or the maximum operating VCC. I might ask you to find the minimum VCC or the nominal voltage, okay, supply voltage. So this is where you're going to look, is under this recommended operating conditions. So you're going to have to scroll down. It might be on the second or third page of the data sheet where you guys are going to find this, okay? Same with finding the high level input voltage, low level input voltage. I'm going to ask you 1 or 2 questions on this on your assignment. This is the part that you have to look at, all right? Recommended operating conditions. I might even ask it in the question. What's the recommended operating conditions for VCC on a 74LS32? Something like that. All right, and you're going to have to go to the table and take a look at it. Or I might ask you for the nominal voltage, which in this case would be 5. The max voltage would be 5.25, and the min voltage would be 4.75 if you were to read, and interpret the data here. I might ask you something about temperature on it as well. Okay, we can look at the electrical characteristics. Okay, it's just going to be pretty much problem specific what I ask you as far as those go. Okay, so just know that all this information comes off the data sheet. So I might ask you something about the PLH or the PHL. Okay, I might ask, what's the max or the min of that. So those are our switching characteristics. Okay, our propagation delay. How long, when we're talking about switching from rising edge to lower edge, or those kind of things. Okay. So physical dimensions. There's a question on your assignment that asks you about physical dimensions. Okay, and we zoom in and we take a look out. Okay, physical dimensions. The question I'm going to ask you is you need to be able to look at that data sheet and tell me how far it is from one pin to the next pin. Not the entire pin, but if we take a look up here, it's the drawing in the upper right hand corner. All right, and you can see like all the different dimensions. So you're going to be able to take a look at that and get the correct dimension that I asked for. Okay, so very, very important. And then in the bottom right hand picture, all right, I've been telling you guys all along, right, the little half moon, the crescent moon, remember that's always a good indicator. Everything has to be turned the right way when you guys did your soldering, but that indicator always tells us where pin 1 is. And that's why when we did our breadboarding, I wanted you guys to make sure that you lined up all the pins so that those little half moons all went in the same direction. All right, that way it makes it easy for you when the first step I told you in breadboarding is to do all the power and all the ground on the chips. Very, very important stuff. All right, but as you go through this, you're going to pull up some different data sheets from different manufacturers for AND gates, OR gates, inverters, maybe an XOR, XNOR, maybe something that's a 4-input AND gate or a 4-input OR gate. And you're going to have to know the numbers of it, and you're going to have to be able to look at the data sheet literally to answer the questions on the homework assignment. But everything that you're looking for is there. Okay, I'm going to be a little bit vague because I want you to actually, dig in deep and find the solution and actually study the data sheet. So it's very important that you understand these, so it makes a lot more sense what's going on when we're breadboarding them and how you're going to troubleshoot them later on when you breadboard and you have a mistake. Alright, as always, email me with any questions or ask any questions in class. This one, this is an assignment that you're not going to be working on physically in class, but I want you to make sure that you know how to do all this. So you do have a homework assignment on this, but I'm not going to really give you class time for this one. This is more of an outside of school on your own type of assignment here. So anyhow, guys, I will see you in class. Take care.